talking about Coulomb's law. Okay, this Coulomb's law, which is concluded or founded or discovered by Charles Coulomb. He measured the magnitude of the electric forces between two small charged spheres. The force is inversely proportional to the square of the separation r between the charges and directly along the line joining them. The force is proportional to the product of the charges Q1 and Q2 on the two particles. So, written as mathematically written the Coulomb's law, it looks like this, okay? So this is a force. Usually people call the force between two charges as Coulomb force. And this constant we call Coulomb constant. And this is the number for this Coulomb constant. For this epsilon, usually we have a specific name called permittivity of free space. All right. So this is Coulomb's law. So there is something we should talk about Coulomb's law. We have to remember the charges need to be in Coulomb. When we do this calculation, the unit for charge has to be in Coulomb. The unit for distance will be in meter. Okay, then we will get the force in Newton. So this is something important. This epsilon is the smallest unit of charge. I'm sorry. This E, this is not epsilon. Well, basically, they're different. This one called permittivity. This is called epsilon. This one is E. E is the smallest unit of charge. Okay. This is charge of one electron. The electron is 1.6 times 10 to the negative 19 Coulomb. So 1 Coulomb. So you divide it by 1.6 times 10 to the negative 19 on the both sides for this equation. Then we'll get 1 Coulomb equals 6.24 times 10 to the 18th electrons, or protons. So 1 Coulomb needs this many electrons or protons. Typical charges can be in micro Coulomb range. So normally, this number, 1 Coulomb, is very large because 1 Coulomb needs a 6.24 times 10 to the 18th electrons or protons. So typical charges will not be as large as 1 Coulomb. Typical charges can be in the micro Coulomb range. Remember that the force is a vector quantity. This force is a vector. Basically, the force here, remember that, the force is directed along the line join these 2 point charges. So this is the direction of the force. Okay. Anyway, we've talked about what's point charge. Okay. We've talked about what's Coulomb's law. Then we talk about these constants. We talked about the Coulomb is a large number, 1 Coulomb, because needs 6.24 times 10 to 18 electrons or protons. Then let's do a very quick summary. For one electron, the charge is 1.602. Normally, you just need to memorize 1.602. The rest of the significant digits, if you can remember, that's cool. If you can't, well, it's okay. So 1.602 times 10 to the negative 19th Coulomb. That's a charge for one electron. But the mass for electron is really low. It's 9.109 times 10 to the negative 31 kilogram. For proton, same amount of charge, but with a positive number. So for electron is negative, this number. For proton, this is positive, this number. But the mass for the proton, which is much larger than the electron. So electron is very light. Look at this. For a proton, basically is I would say 1,000 times of the mass than electron. And for neuron, the charge is 0. That's why we call this particle neuron. But the mass, which is similar to the mass of proton, the electron and the proton are identical in magnitude of their charge, but very different in mass. The proton and the neuron are similar in mass, but very different in charge. Let me ask you a... Yes, Raman asked the question, is every force is vector? Yes, every force is vector. Every force is vector. Every force is vector. Excuse me. I do have a quick question. What's the proton and the neuron get together? What they will form? Well, it's atomic nucleus, right? Atomic nucleus. I think you should be able to know that if you've learned in this vector nature of electric forces into that Coulomb's law. In vector form, the Coulomb's law can be written as something like that. Okay, let me show you a picture. This is charge Q1. This is charge Q2. And then let's assume they have same sign, which is positive. So we have this Q2 has a force from Q1. So the Q1 will put a force, repulsive force on Q2. Okay? So F12. Pay attention to this, the subscript. So
what I'm going to talk about is I'm going to write this Coulomb's law in the vector form. Now, this is the picture I was talking about. Again, this is the picture I was talking about. So this is the force vector, from Q1 on Q2. And so the direction is, because it's repulsive force, so the direction is going this way. And this force is from Q2 on Q1. Okay? So we have a different subscript, which represents different meaning. Okay? So let me write this F12. F12. And then the magnitude of force we've already talked about. The magnitude of force is proportional to the product of Q1 and Q2 because they're all positive. So the product is still positive. And it's inversely, the magnitude is inversely proportional to the distance, r squared. And then the proportional constant is Ke. Now, pay attention to this. What's this r hat 1, 2? R hat 1, 2 is a unit vector. From Q1 points to Q2. From Q1 points at Q2. So this is a unit vector. Okay, unit vector. So I have a vector F12 equals to this one. Let me ask you a very quick question. What if I apply absolute value on both sides? If I apply absolute value on both sides, we will have something like that. Let me try to write on the screen. Hopefully, we'll be able to do that. So if I'm going to write absolute value for this F12, sorry, F12, something like that, and Y2, this is F. So I put absolute value, then equals to the absolute value for this Ke times Q1 times Q2 divided by r squared times, this is a vector, r vector, which is a unit vector, from 1 to 2. And for this one, because this is positive, Q1, Q2 is positive, this is positive. So this is equals to, and times, this is R, one, two. Because this is unit vector, so this equals to, so we come back to the original, disappeared. Sorry, I don't know where it is. Somehow it was disappeared. Anyway. It's here. So let me put it here. Okay. So this unit vector, I hope you will be able to get the sense what this unit vector means. The unit vector represents the direction of this force. Okay, so R hat 1, 2 is a unit vector directed from Q1 to Q2, which is really, really important. Really, really important. Okay. The like charges produce a repulsive force between them, so that's no problem. Now, let's say electrical forces obey Newton's third law. So the force on Q1 is equal in magnitude and opposite in the direction to the force on Q2. This is two objects. So the force from Q1 on Q2 will be the same magnitude as the force on Q1 from Q2. But the direction will be different. So F12 is this direction, then F21 is this direction. Okay? So the force on Q1 is equal in magnitude and opposite in direction to the force on Q2. So we have this one. So F21 equals to negative F12. With like signs for a charge, the product Q1, Q2 is positive. So the force is repulsive. Right? Now you know. Now you know. Now, let's continue a little bit. What if the 2 point charges are separated by a distance of r, but with a different sign? So the unlike charges produce an attractive force between them. With the like signs for the charges, the product Q1, Q2 is negative. Look at here. If I have a Q1 and with a positive, and the Q2 is negative, so these are unlike signs for these two charges. So Q1 times Q2 is negative. When a force is negative, then it's attractive. Why? Let's have a look. Let me put this one. Let me put this equation. Move this equation on the slides here. Now, same here. So F12. Is F12 the same direction as R12 or the different direction with the R12? I have a question. Does the F12 has the same direction as R12? Yeah, give me some feedback through text message. No, okay. Iradukunda says no. That's correct. That's correct. Simply R12 is still the unit vector, which is points from Q1 to Q2. Then, because the Q1 and the Q2, let's say, why? Let me ask you more question. Why? Because Q1 and Q2 has different sign. Yeah, because Q1, Q2 has a different sign. So the magnitude here has the negative sign. So which means F12 has the opposite direction with R12. Okay? Yeah. But the equation still holds. The equation is still the same. So shall we put the, let's have a look. So this is a Coulomb's law. The Coulomb's law here. We use the Coulomb's law to describe the situation for the charges are of the same sign. And then, if I replace the charge with the opposite sign, the equation still holds. We don't have to change this equation. Okay? Because R12 is still from Q1 to Q2. But, but the Q2 times Q1 is negative. This means F12 has the opposite direction as R12, like we draw it on the picture. So the equation still holds, all right? Although the different condition, but the equation still holds. So let me continue. So the sign of the product Q1 and Q2 gives the relative direction of the force between the Q1 and the Q2. The absolute direction is determined by the actual location of the charges. What if there are multiple charges? If there are multiple charges, the resultant force on any one charge equals the vector sum of the forces exerted by the other individual charges that are present. Remember to add forces at vectors. The resultant force on Q1 is the vector sum of all forces exerted on it by other charges. For example, if 4 charges are present, the resultant force on one of these equals the vector sum of the forces exerted on it by each of other charges. All right. Then somehow, let's have an example called a zero resultant force. We have a negative charge. We put this charge in between of 2 positive charge. Where is the resultant force equal to 0? The magnitude of the individual force will be equal. Then the resultant force on this negative charge will be 0. All right. So if the Q1 and we can analyze this sort of questions. We can do a calculation. If Q1 equals Q2, then this Q3 has to be in the middle of Q1 and Q2. If Q1 and Q2 are different in magnitude, then what's the X? can we calculate the x by Coulomb's law? How do we calculate by Coulomb's law? Let me do this very quick, okay? Let me do this very quick. So we have force from Q1 on Q3, which is F13, this direction, because there are two different signs. We have force from Q2 on Q3 on another direction, because there are different signs. So let me write in this equation window. Let me do this. So what's the magnitude of F13? So the magnitude of F13 equals, let's say, K E Q1 times Q3. And then what's the distance between Q1 and Q3? See, I was trying to calculate this distance, x. Of course, you can make this one is x, this one is 2 minus x. But in our graph, we've already made this one x, so this one is a 2 minus x. Because we know the distance between Q1 and Q2 is 2 meters. So this one should be 2 minus x squared. And what's the magnitude of 2, 3? Equals KE Q2 times Q3, and this is x squared. So in order for this charge has a zero resultant force, what we should do is F13 equals to F23. And then we can solve for x. Now, it's very easy to solve for x, so we can cancel the KE with each other. We cancel Q3 with each other. So what do we get? We get this equation. We cancel Q3. We cancel K, we cancel Q3. Alright? So we got this. And then what's next? Because we have to solve for x. So that's divided by, say, let's move this Q2 on this side. And let's move. So we move this one to here, and we move this Q2 here. Then, what else? What can we do? Since Q1 and Q2 are both positive, so we can do a square root. So let's do this. So the square root, then we can get rid of this square. Alright? Then we can solve for x. So what's the x? Now we times x to this side. So we times x. So this one is 2 minus x. Right? We can move this x to this side. So x plus 2. So we can factor x out. We got this. So we have result for x. Alright. So what's the result for x? X equals to 2. Let's say 2 divided by this one. This is how we do the calculation for problems like this. Okay. Now you know how to solve problems like this. Hopefully, okay? So now you solve the problems like this using Coulomb's law. So this is one application for Coulomb's law. Now, the more we can talk about, okay, the more we can talk about. Say like this one, electrical force with the other forces. Example, okay. The sphere are in equilibrium. They're in equilibrium. Why they will be in equilibrium? Can you tell me for Q? For Q, left side. Say for Q, left side. How many forces on it? Can somebody tell me? For Q on the left side, how many forces on it? What are they? Just send me a text message. Send me a text message. Say for this Q. How many? So you still there? Anyone? Are you still there? So you're 2, no. 3 forces. It's one force is a pulling force from the rope. Gravitational force and the repulsive force from this Q. So for this Q, we have 3 forces. So, okay. Do you know how to draw the free body diagram? Alright? You may want to draw the free body diagram after our lecture. Then electric force with other forces, like say we have a pulling force T, we have a gravitational force mg, we have a force from another charge particle. We have from another charge particle on it, defined by Coulomb's law. Alright? Because they're in equilibrium, so you have to calculate in which condition these 3 forces, add them together, is 0. Okay? So which, I believe the time is over. I'm sorry. So I will talk to you next time. The time is over. The time is up. Okay. Alright. See you tomorrow. Okay. See you tomorrow. Okay. See you tomorrow. Alright. See you. Have a nice night. Good night. Okay. Good night. Bye-bye.